Hello, my name is Jorge Carlos Medina, leader of the embedded systems team in charge of implementing the microcontroller units.
Hello, my name is Andres.
Hi, my name is Pablo and I'm in charge of electronics.
Hello, my name is Abiel and I am a developer on the RoboBoat embedded team. I also worked on some of the PCB design.
Hello, my name is Marcelo and I am part of the electronics team.
The electronics of the VantTec 3 USB have been pretty consistent throughout most of our competitions, since they have been functional enough for being able to run all systems with minor and really infrequent issues during physical tests.
Our electronics in previous seasons had relied on 5 power sources, one LiPo 12-volt battery for the motors, one 12-volt lead-acid battery for the Jetson, and one USB power battery for the microcontroller. Two 6-volt lead-acid batteries were also used to power the peripherals on the boat, such as the SET camera and the Velodyne LiDAR.
We originally used one power relay, used as an emergency stop, connected to the kill switch located at the front of the boat. When it's triggered, this cuts the power to the motors. These motors were powered and controlled by electronic speed controllers, and controlled by Arduino Nano. The Arduino received the data, the Jetson TX2, via USB serial. The Arduino was also connected to a Taranis X9R radio receiver for deliberated control. We also used XBs to communicate with our ground station.
Arduino was originally used as it is a microcontroller with a very accessible price, great availability, and is easy to work with many applications. It has the role of handling the ESC drivers and also of mathematically processing the signals given by the hydrophones.
Even though it was functional, during our last physical competition, we had a major issue that was pinpointed down to the then-used microcontroller, the Arduino Nano. This issue prompted the importance and motivation to change the system.
This season, we decided to take on the challenge of reimagining our electronic system, featuring a new PCB design which was created to provide better, neater, and more stable connections inside the hull. A new microcontroller system for motor control, signal processing, and sensor data collection was implemented. This is due to the fact that during our last physical competition, we found that the Arduino that we were using did not achieve the expected performance.
Health conditions were quite a handicap for developing a physical system, as we weren't able to visit our lab not even once, where we store all our hardware.
So, we decided to take the next approach. If the conditions allowed and there was still enough time, the designed electronic system would be implemented. Also, there was not a lot of risk involved, as we can always rely on the already implemented design from previous competitions.
Another aspect to mention is that we also participate in the RoboBoat competition, so we have decided to create a shared design between our boat and submarine, thanks to all the similarities they share. These being the motors, sensors, batteries, and the fact that in both we use Jetson TX2 for perception processing, obstacle avoidance, and guidance navigation and control algorithms.
For the same reason of participating in both competitions, we realized that the processing power provided by the Arduino was not good enough, taking into account that the board also doesn't provide any advanced debugging tools like performance estimators. We decided to switch to an STM32 platform. This way we have access to better debugging tools and more processing power in case we want to implement any computer-intensive programs.
As we step up our microcontroller from an Arduino to an STM32, the power constraint was to maintain the same power capacity while achieving a better work performance from the unit. And to accomplish, the later we transitioned to a real-time operating system.
Another factor in the unreliability of our previous iteration was the communication protocol between the microcontroller and the Jetson. Previously, we were using USB serial communication, but we found that it was prone to interference. To improve on this, we decided to switch to using CAN, which is an industry standard proven to be able to withstand any electrical interference.
The achievement we expected the most was to maximize the computer resources at all times, and being able to effectuate the time constraints needed for sensors like the hydrophones. Something else really important was the capability of controlling the boat's thrusters while handling all other tasks simultaneously.
As the pandemic continues to be a latent problem, it was impossible to do physical testing. This is due to restrictions to obtain the hardware from the boat at our institution. It was not until a few weeks prior to this competition that we were able to gather the materials.
Due to this factor, the improvements of the electronic systems could not be fully tested by the time of the competition. So these improvements are on paper but require further validation from a real-life environment.
For testing and development purposes, the STM32 microcontroller will allow us to use tools that allow the measurement of power consumption. This will also allow us to optimize the power usage of our processing tasks. Also, the sampling speed that this microcontroller provides is more suitable for the sampling rate of the sensors that we use, given that we plan to implement signal processing for 3 hydrophones running on our microcontroller.
The FreeRTOS environment implemented allows us to achieve better performance metrics when compared to previous implementation. This is due to the operating system allowing us to achieve a multitasking environment on a single processing unit by using threads. For example, if a thread stalls because it's waiting for an interrupt, then another thread can take its place on the processing unit until the event occurs and the interrupt happens.
This enables us to have fewer performance drops and maximize the resources we have. We can now achieve a greater processing power, much better than compared to the past iteration, where wait times affected real-world performance.
In order to achieve an optimal performance, the implementation of parallelization in our programming helps us get better power consumption estimations using the STM32 IDE, which makes up for an auxiliary solution as we couldn't do any physical tests because of the pandemic.
Working with KitKat as our main design tool, we were able to share any modifications within our team by adding any changes to our repository. Synchronization of our work became an important part of managing our efforts and allowed us to work at a fast pace for our iterations.
We included 8 ports for thrusters, so that if any of the controllers of these thrusters were deborn, we can change the port quite rapidly. We also added a fuse for each one of them to prevent any undesired situations. Both PCBs utilize the STM32 microcontroller as a logical controller, and both have the same spaces for their system-specific sensors. And in case that the system where we're implementing the PCB does not require one of these system-specific sensors, we just don't solder it and that's it.
By taking advantage of the space saved by reducing our electronic size, we can add current sensors for our thrusters. Now, we can rapidly identify any issues that may occur on any of our thrusters, such as faulty thruster or even plant stock on any of them.
With this change, we reduce the power consumption, hence the use of batteries, saving on weight and space. This way, we can expect a longer runtime from our robot. We used 5 batteries in previous models, which add unnecessary weight and made charging an inconvenience. Now we are using only 2 LiPo batteries, which make everything simple. In brief, we are pushing the efficiency limits of our boat.